Yeah.
Yeah.
Does this work now? Maybe.
Try again.
Yeah.
Does it work?
Yeah.
So Anand, yeah, you wanted to say something.
People in the audience, we plan a little get together at our place tomorrow. It's not right. It's not. First of all, I'm aware that this COVID situation, people may feel uncomfortable, and so we're trying to keep windows open. Everybody in this institute has to be vaccinated. So anyway, we're aware of the issue, but we wanted to do something. And also, it's not a birthday party, right? It's a party. It's a year party. So it's not a birthday party. So it's just simply, it's a good opportunity to get together, people feel comfortable, and so thank you to everybody for this nice program. So that's, yeah. The address is, maybe you can write it, is 29 Sullivan Street. 29 Sullivan Street. Okay, Sullivan, 29 Sullivan Street. Should I write it down? Sullivan, S-U-L, Sullivan, 29 Sullivan Street.
And when?
Around 7-ish. We'll try and have some wine, cheese, snacks. Maybe it's not going to be a major thing, but we'll have some things available. Just bring some wine, okay? If you bring hard liquor, I like the height of It'll be hidden somewhere. Sort of come along, Brian, for a couple of minutes. Okay, so tomorrow, yeah, and it's a bit more information needed.
Can we be here?
Yeah. 29 Sullivan Street. It's due south here. From Huron Street all the way down to 150. Okay. We'll open there's a patio there. We can open the windows and try and keep it safe, but I mean, it may be a lot of people there. So if you don't feel comfortable, it's okay. I may announce it again tomorrow. So sorry.
Yeah. Okay. So my humble goal today is to first recall the definitions. That's the first thing. Discuss Kim Foking. And finally, I want to prove King's lemma. King's lemma for King. Okay. So and to see some application and okay, that's what I plan to do today. Okay, I hope I get to it. I hope I didn't prepare too little though. Okay. Yeah. So first I want to recall the definition. So definition. Phi, a formula phi of xy has SOP1 if there is a sequence which looks like A eta in to the less than omega. Okay, so each element in the sequence is a node in the full binary tree, such that let's call it S. Okay, S. such that one, so the consistency requirement, if eta is a branch, then phi of x a eta restricted to n is consistent. Okay, so along the branch we have consistency, and two, the inconsistency part. Oh, thank you. Okay, I promised myself to try to be orderly with the forks. So well, okay. This is the consistency requirement. The inconsistency, if S and T are in are both nodes in the tree, and T equals the meet of S and T, and then concatenated with 1, and S is at least the concatenation with 0, then phi of x as and phi of x at is inconsistent. Okay. The point is we have a binary tree. Okay. So if we pick any branch in the tree, then it will be consistent. This will be consistent. And on the other hand, if we take two something like this guy and this guy, then they will be inconsistent. Okay, but I'm not saying anything about I'm not saying anything about this guy, and I'm not saying anything about this guy. Okay.
Just like you said last week.
What?
Just like you said the same picture last week.
Yeah.
I saw it yesterday.
Yeah, so people who saw it yesterday don't need this reminder. Really? Okay, so yeah, I guess I don't have an excuse. So okay, so this is the definition, and now let's do something I didn't do last week, which is to see explicitly, is it obvious that this implies that if T is simple, then it's NSOP1? I was going to maybe explain why. So is a remark which is easy to see just playing with these trees a little bit. If T is simple, then it is NSOP. So what I want to do is to start with. So I want to prove the contrapositive. Okay. So the contrapositive would say if T has SOP1, then T is not simple. So proof. We prove that SOP1 implies not simple. And what does not simple mean? Just the same as saying having the tree property. Okay, that's what we're going to show. So I want to construct from a tree, from a binary tree like this. I want to construct an omega tree, omega binary tree, which will witness the tree property. Okay. So I think that in this case it's easier to draw it. So we have the we have the binary tree. Okay. So this is the zero. This is the 0 part. Okay. And now we're going to look at these guys. Okay. This is just like, for example, this guy is 0, 0, 1. Yes. I think, or maybe 0, 0, 0, 1. Okay. So, okay, this is 0, 1. This is 0, 0, 1. This is 0, 0. Okay. So these are elements in the binary tree. And now you see that each two of those is inconsistent, right? If you take this guy and this guy, they will be inconsistent because their meet is exactly this guy, and this is exactly 1 after the meet, and this is continues to 0 after the meet. Okay, so each of those are two inconsistencies. That will be this will be the first level in our tree. This we will choose the tree such that the first level in our tree will be this level, and then we want to continue. So from each of them, for each of them, I will look at okay. Let's look at this guy because it's the last one, so I have a place to draw. So from each of them, I'll just look at this. Okay, and here also. Okay, so this will be the second level starting from this guy. Okay, and again, each two are inconsistent here. Okay, and each branch is consistent. So this drawing can be made completely formal and there's no problem at all, but I'm just explaining how you can see you can make a binary tree into a full omega tree by this kind of games. And you can even get two inconsistencies instead. Yeah.
So can you draw the corresponding picture?
Yeah, we don't need it. I only need one direction. I'm given a full binary tree, but all I need are things that start with like 0, 0, 0, 1, and then a bunch of other zeros, and then okay. I mean,
I'm not sure. I mean, what is the omega tree? I'm not sure.
okay. So the first, okay.
That is the question.
Okay, so maybe I'll try to actually write it. I think I did try to write it. Yeah. So these are AS. Okay. So I want to define BS, which will be the omega tree. Okay. So BI, a singleton, like this means just a sequence I. This will be A 0 to the I 1. Okay. And then Bij will be A 0 to the I 1, 0 to the J 1. Okay, and so on. And I can continue like this. Okay. Yes. Okay, now let's look a little bit closer at this definition of SOP1, and we'll play with it a little bit more. So what happens by compactness? We can assume we have if phi has SOP1, then there is a sequence A eta. Yeah, now it makes sense to call it eta actually. Eta in 2 to the less than kappa, where kappa is any cardinal with the same properties, with 1 and 2. Before, where kappa is any cardinal. So if we have a tree, we can make it as high, okay, as high as we want. Okay. Let's see what this gives us. So let's choose a particular kappa. Let's take kappa to be 2 to the t plus. Okay. You'll see why in a second, I hope. Okay, so right. Okay, so we start to draw the tree, and it's going to be very similar. Let's look at so the tree is A. Yeah. So let's look at A 0 to the alpha 1 for alpha less than kappa. Okay. Let's look at this sequence. Okay. So again, this is the sequence. I'm going over these guys, and I'm looking at it. Okay. Okay. So because kappa is so big, there must be by pigeonhole there are alpha and beta such that A0 alpha 1 and A0 beta 1 have the same type. Right? Because we chose kappa so big that for many big set of size, I mean, these are finite totals. So the number of types is at most 2 to the t, but we have 2 to the t plus. Okay, let's call these guys. Okay, that's going to confuse the indices a little bit, but let's call these guys alpha, alpha 0 and beta 0. Okay, I hope so. Okay, all the indices can really be confusing. Okay, but yeah, okay, now I want to continue. So now I'm looking at the sequence A0 to the beta 0, and then 1, and then 0 to the alpha. Looking at this sequence now. Okay, so this means going here, this is alpha, and this is beta, alpha 0, beta 0, and I'm continuing here. Okay, and again, I can by pigeonhole, there are by pigeonhole, we can find alpha 1 less than beta 1, okay, such that A0 to the beta 1, sorry, A0 to the beta 0, 1, 0 to the alpha 1 has the same type. Oh, yeah. I forgot. There's a 1 here. Yes, thank you. It's the same as this. So it's supposed to all end with a 1. Yes. So this has the same type as A0 to the beta 0 again, and 1, 0 to the beta 1, 1. Okay, all of this, but now we can say even more than having the same type. Let's say over these two guys, over, let's call this guy C0 and C1 in order not to, okay, over C0. C0, C0. Okay, C0, C00, C01. Okay, there's so many indices here, but I hope it's not confusing. So I can even make it that it's that it have the same type over these two previously chosen guys. Okay, because still there's boundedly many types and there's too many guys. Okay, so what can we know now? Now we have these two guys. So let's call this guy C10 and this guy C11. Okay. So what can we say about the relation between? So we have so far we have C00, C10, and C01 and C11. This is what we constructed so far. I want to just say what can we say about this. So what I claim is that I claim that this. So first of all, this and this have the same type over these two, right? So these guys, they have the same type over these two, and these guys have the same type over the empty set. Okay, so the first is C10 is the same type as C11 over C00, C0. So that's the first thing we notice. Second thing is that phi of x C11 and phi of x C01 is consistent. Is this true? Okay, because C01 ended with beta to the it ended with beta, it ended with beta 0 and then 1. And C11 started with beta 0 and then 1. So they all continue the same branch. Okay, so this comes up. So this is in the drawing. This is C11, C01, and this is C11. Okay, so they continue the same branch, so it's consistent. So this is true. And the second one is phi of x C10 and phi of x C00 is inconsistent. Right? Because in now, if we look at this guy and this guy, then they look like this and this. Okay, so the meat is exactly this, and okay, it's exactly by the SOP1 requirement. So we have these two things. This is consistent and this is inconsistent. Now I stopped doing it after 2 steps, but I can continue, right? There's no continuing. Yeah, now I'm going to this board. So continuing, what we can get, we get a sequence which looks like C. Okay, so C I for I is less than omega and j less than 2. Okay, such that C I0 has the same type as CI1 over C less than I, and then every j, so C less than I. So CI0 is the same type as CI1 over the previous guys. Then just copying what is there. Oh, wait, there's 1, 2, 2. Somebody should have, okay. And 2 is that phi of x C1I, what is this correct? Yeah, CI1 well, this is consistent. So going over the 1 column, I get consistency, and 3 phi of x C. So this is supposed to be I0, I less than omega. This will be 2 inconsistent. Okay. Do you agree? Is that okay? So we got this nice we got this nice thing, which is somehow, I think, more familiar. This kind of phenomena is more familiar to model theorists than this strange thing where you choose only going from the right. Okay, there's kind of choices involved, and here, like, it seems like more. You have an array of you have an array of omega times 2, and the first column is consistent, or the second column is consistent. In this, the second column is consistent, and the first one is 2 inconsistent, and also you have this extra condition that the first one and the second one have the same type over all the previous ones. So let's call that. So this justifies the definition. Okay, so definition and so suppose, okay, n SOP1 array for phi of xy is a sequence. So you have C, I want to say the same thing, Cij, I less than omega, j less than 1. Such that, but I think I want to switch the 1 and 0 because later I'll be, I think I'll switch it. So it's better to switch it, yeah, starting from now. What? Yeah. So such that Ci0 has the same type as Ci1 over C less than I, and for life. 2, I want, as I said, I want to switch 0 and 1. So phi of x C0I is consistent. And 3, phi of x C0 C1I, I less than omega, is inconsistent, but before it was 2, but 2 is 2 is okay. Here we got 2, but in the definition there's no. It doesn't seem natural to just say restrict ourselves to 2 for some case. Okay, so this is
I0 and I1.
what here?
The C's.
What's the question?
Instead of C0.
Oh, I mixed it. Yeah, it's I0 and I1. Yes, thank you. Yeah, okay, so this is a definition, and now there's now what I want to do is to try to prove that that SOP1 and having an SOP1 array are equivalent notions. Okay, that's what I want to show now. What we showed so far, okay, we just say what we showed. So we showed if phi has SOP1, then phi has an SOP1 array, even with k equals 2. Okay, so this is what we have. Okay, so now I want to prove the following. So the theorem is the following are equivalent. One, T has SOP1, and 2, some phi of xy as an SOP1 array. And what we proved is one. So we have one implies. But I am going to prove it in the level of the theory because we don't get the same formula. I don't know that we can get the same formula. So it's going to be it's going to be once I have this, then the formula which has SOP1 would be would be a Boolean combination, I think, of phi. It would be even a conjunction of
Even if you allow k equals 2.
yeah, of course, that's the question. Yes, you're right, but let's see from the proof. I think that I'm right. Okay, and you'll be able to check me. Okay, so for this theorem I need so the main issue is to prove so we want 2 implies 1. So for this I'm going to prove the following lemma. And this is a kind of a technical lemma. So suppose we have some sequence C I J I less than omega, j less than 2, such that Cij can be written as Dij Eij. Okay, every guy in this sequence is itself a pair. Okay. Assume also suppose we have these formulas chi1 of xy and xz. We have these two formulas maybe over some parameters. And let's say psi of x, y, z is P1, is the conjunction of P1 and P2. Okay, these are all assumptions. Also, assume, we're going to have more assumptions. Assume one. So EI0 has the same type as EI1 over C, the parameters over which Hi1 and Hi2 live. C less than I0 and E less than I1. I'm going to repeat this once I finish writing. 2 psi of x C I0 is consistent. And 3, if j is less or equal than I, then Hi1 of x di0 and Hi2 of x ej1 is inconsistent. Okay, so okay, all of these assumptions, then T as S of P1. Okay, and actually the witness would be psi. Okay, let's go over it again.
But this never had independent interest other than proving the theorem.
No, I don't know of any such interest.
Is it used again somewhere?
No, not by me, at least. At least I don't know of any usage of this. Yeah, maybe it will be. But right, okay. So I just want to maybe explain what's going on here. We have this we have these two things. See the CI0 and CI1, and all the CIs themselves can be written as DI0 DI1. So DI0 EI0 and DI1 EI1. Okay, so and we have so let's make it specific. Let's take 3. Okay, and then so this is D20, D20, D21, D21, and wait, 1, 1, D1. Okay, so and there's also 0, D00, E00, D10, E A1. Did I make it correctly? No, this should be 0. Okay, so what are the statements here? That if you go first of all, that if we look at the e's, okay, so this guy and this guy, they have the same type over what? They have the same type over this, the C part, okay, and the E part. But I don't mention the D's at all. The D1 I don't mention.
What is C?
So C is just a pair. So C is everything. C Cij is the pair Dij Ei.
There's a base called C.
Oh, capital C. Yeah, capital C is somewhere. Yeah, there's also capital C somewhere. Yeah, and yeah, right. So it's like in the background. Yes. So what the statement is, these two have the same type of everything in the square, and that's the first thing. The second thing is that if we look at a column, then we have consistency alongside. So here we have consistency. If we look at the 0 column, okay, psi is just the conjunction. Okay. So this and this and this and this, all of this is consistent. And what about the inconsistency? we have that j is smaller than I. So yeah, like for example, let's so like for example, this guy one yeah, what did it say? So EJ1. So yeah, so this guy is inconsistent with this guy. Okay. Yes. 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 I think I did it correctly. Okay. So this is inconsistent with this. If we take some guy from this column, from the E column, and we compare it to some guy from the D column, but above it, then we get inconsistency. Okay. Yes. So, then okay. Let's see how the proof works. Okay. So. Okay. So proof. So first, we may assume that this entire thing, Cij, so Ci less than 2. So I can assume that this you can order it by Z, and I can assume it's indiscernible. I'm not sure this will be used actually. I'm going to use that it's ordered by Z.
So you mean the pairs are indiscernible? Or
No.
because
Yeah, the sequence of pairs. Yes.
sequence of pairs.
Yeah, the sequence of pairs.
No, I mean the pairs of Ci0, Ci1, or
No,
you mean
no.
quadruple?
So every element I is a pair.
It's a quadruple?
It's a quadruple, yes.
Okay.
It's a pair of pairs, so it's a quadruple, yes. So these are 4 guys. So the whole thing is indiscernible over C, and it's also ordered by Z. We can assume that compactness. This doesn't lose anything. All of this can be written as a type, and we can realize it. And so we can assume it. Also, let's assume C is the empty set, because we can just put it in. We can just plug it into the things, and it will still work. Okay, so let's assume it. So what we're going to do is to construct a tree. We want to prove SOP1. So we're going to construct a tree. That's how we prove SOP1. Yes, okay. So we construct a tree, and the tree will be CS and S 2 to the left n. So it's going to be a finite binary tree for each n. N, forgot. So for each n, we're going to construct a tree, such that, and now I'm going to list 3 properties, and hopefully it will be fine. So property 0 is that. Okay, maybe I should draw it. I can erase this, right? This is another drawing, so I don't know. Okay, so now I'm assuming that it's ordered by Z. So I have this. Yeah, let's look at this like this. We have C. C minus n minus 1, 0, C minus n minus 1, 1, and here we have C minus n. I did it correctly? Yeah. So it's going to be clear what these numbers. So this is minus n0, this is minus n1, minus n minus 1, 0, minus 1. Okay, so this is, it goes like this. Okay, and of course it continues here, but something special is going to happen here. So and here I want to construct a tree such that the first requirement is that if I look at this tree, so C empty set, C0, okay, C0, 0, and then up to C0 to the n minus 1 is actually the same tuple as C minus n minus 1, 0, yeah, until C0. Okay, so just to be sane, there are n guys here and there are n guys here. So this makes sense. Okay.
What about minus?
Yeah, because everything is in Z.
Oh, I see.
These are all integers. Actually, I don't need the positive numbers. I only need the negative numbers, but still, it doesn't matter. So here, yeah, everything is in Z. So here I have C minus n minus 2, 0, right? C 1. And what I'm saying is, and it goes all the way to C 0, 0. So what I'm saying is the first guy here, this is going to be the first, this is going to be the 0 path in the tree. Okay, that's what I'm saying. Okay, 1. So this is 0. 1 is, if I take S for all S in 2 to the n, if I look at C T less than S, so this is a path in this tree. Okay, this is just a path in this tree, in this finite tree. This is going to have the same type as exactly as the 0, as the 0. So they all have the same type as C minus n minus 1, C 0. Okay. So all of the paths, they will have the same type. Okay? We're going to build a tree such that this is the 0 branch. We have other branches, and they all have the same type, but over what? That's important. So they're going to have the same type over C less or equal than n minus 1, then minus n minus 1, 0, and E minus n minus 1, 1. Less or equal than this. So yeah, less or equal. Yeah. So they're going to have the same type. All of the passes are going to have the same type over everything in the C, but in the C0, everything from here, and also everything in the E, which was yeah. Also, yeah. Remember that this guy is D and E, so this is going to be they're going to have the same type over whatever is written here. Okay. Okay. Sorry, not. Oh, so this. They're going to have the same type over this. Because this is a minus n minus 1. This is already. So this is going to be the root of the tree. This guy is going to be the root of the tree. And they're all going to have the same type over the thing before. Okay. And then number 2 is the inconsistency. So if S and T are incomparable, and yeah, so T is S wedge T and then 1, and S is at least T wedge S and then 0, then we have inconsistency. So we don't have equals. So yeah, I'm going to write it again. Yeah, here, so it's S, so again, S equals S wedge T, sorry, at least S wedge T, and then 0, and then T equals S wedge T, and then 1. Under these conditions, I'm going to ask that then T1 of X ds and T2 of X et inconsistent. Okay, that's okay. That's on the assumptions. Okay, yeah. So yeah, so we're going to build a tree. What? We're going to build a tree, a binary tree of height n for each n.
So DS is just the D part of C.
Yeah. Sure. Right. Yeah. Remember that each C is a pair of D and E. So it makes sense to have, okay, so the same, when I say DS, I meant the corresponding D part in CS. Okay, so in particular, if I look at this, in particular, then we get that psi of x CS, psi of x CT inconsistent. Because a psi was just a conjunction. Itay had more things even, okay? Okay, so this, this gives you SOP1, right? This gives you that if we can do this for every n, then by compactness we get SOP1 because we get that the branches do all the same type as the zero column. And remember, one of the assumption is that the zero column is consistent. So we get all the branches are consistent. We get the second part, which is exactly this, is the inconsistency. Okay, so if we can construct this tree, so let me just show you how the construction works. It's really easy actually. Once you know what you want to do, then the construction is pretty easy. So for n equals 0, there's just, so I'm doing by induction. Okay, by induction. So for n equals 0, there's nothing to do. It's an empty tree. Okay, so suppose I have a tree for n. Suppose we have for n, we have CS. Okay, as above. And I want to construct, we want to define CS prime, let's call it prime, for S in 2 to the less or equal than. Okay, we want to add one to kind of split the tree. Okay, so we'll just define it. So C empty set will just be C minus n minus n. Yeah, we don't have any choice. This is what we don't have any choice in that.
Minus n.
Yeah, now it's supposed to start with C minus n, right? Before it started with minus
So
n.
minus n 0.
Oh yeah, 0. Yeah, the same as above. Yeah. Now also, there exists an automorphism sigma such that sigma maps sigma of E minus n minus 1, 0 is E minus n minus 1. And sigma fixes everything else. Sigma fixes C less or equal than n, then minus n 0, E less or equal than minus n 1. Where we have such a automorphism, that's because of this. Okay, that's exactly the assumption, right? So now we use this sigma. So what we're going to do is we have a tree on the left. We can think of the tree we have already as a tree starting with 0, and we use sigma to get the tree starting with 1. That's the idea. So and then it just works. Okay, so I think I can write it here. Okay, so now just formally how you do it, you just define for S which equals to 0 and then S prime, just define C prime S is C S prime. Okay, you just don't do anything. And for S which equals to 1 S prime, then CS will be sigma of CS. And then you have to check that it works, and it does. Okay, actually I was prepared. I wanted to check it with you, but I think I lost some of you, so I don't want to spend. But it does work. I checked it today. There was actually a typo in the original paper, and I found it yesterday, I think. Paper with Nick. When we proved this, yeah, when we proved this, I think there was a small typo there, and yeah. So yeah, the problem is we added to add here n minus one as well. That the problem in our paper we just started with minus n, but actually it should start with minus one with n minus one. Yeah.
Where do you send back over the things to do?
That I'm what? Oh yeah, because of this, right? I have this automorphism here, and it fixes all this guy.
Why do you use it? I mean, I understand why it's true, but why do you use it?
Oh yeah, I'm using it to show the inconsistency. Okay, to show the inconsistency because I have to start now. Like okay, so now look, this is we have a binary tree, right? We have a binary tree, and this tree, what goes on here, this we already knew. This part we already knew. All the inconsistency and consistency result they hold here, and also whatever happens here is true. But the problem is we have to check this guy and this guy, for example. And for this, we needed that they have the same type over this guy. Okay, so
What?
I think what? So okay, so yeah, okay. Well, now we have to show the inconsistency. Okay, so we want to show that, for example, this guy is inconsistent with this guy. But okay, this guy has the same type as this guy, so I might as well assume. Okay, it's this. But what is this? This is just the original. Yeah, this guy is just one of the original C's that we have. Because remember, the zero branch is one of the original C's that we have, and this guy is the original C1. So it has the original. Wait, it's written here. It has the original E1. Yeah, so this guy has the original E1. This is just C minus n minus 1, 1. Yeah. Okay. Well, okay, it's not exactly that, but it has in it D. It has something which has also yeah, E. So E. It has some other stuff in it, but we only care about the E. The E part is the same. It has some D, some extra D, but we don't actually the D1 is never used here. So we have this E. It's the same E as before, and yeah. So this now we assumed in the induction that everything here has the same type over this. This is what we assumed. Look. So it has the same type over this. So this guy is inconsistent with this, so also this guy.
Oh, you assume a lot more than that, but I guess
I'm not just assuming that it has some type over everything before, but also over like the first, also over the E. That was exactly actually the type of that I found. But yeah, you need to have the same type in order to get still the inconsistency. Okay, so yeah, maybe it's time for a break, and then after the break, I'll just quickly show how to use this lemma to prove the array.
But by the way, this goal here, was it the goal for today or for the rest of the
I thought for today, but apparently not. Apparently not. I thought for today, yes. But definitely for next time, I will definitely finish this and also prove symmetry next. Just leave this one.
Oh, really? Yeah. But it was very much based on that shallow paper. It wasn't, how did you come up with this question? It was simply, but you didn't know the sort of how to do this. Well, we knew in principle theories about this, so I'm not sure we actually knew that maybe to prove that all the examples are simple using characterization. I guess I think when actually using that, it wasn't.
So everybody happy? It's like this break was like everybody stayed here. So yeah, okay. So good. I can continue. So I left this lemma on the board because I want to show how it's used. And for this, I want to give another lemma. So this is lemma 1, but and there's going to be lemma 2, and then from lemma 2 is just a lemma 2 is just a statement that we want. So suppose C0, Ci less than 2 witnesses shows that phi xy is an SOP1 array, where with k, let's say, with some k, and then T as okay, that's right, that's what we wanted to show. Oh, but I call it lemma 2 for some reason. Okay, so just recall what is an SOP1 array. It just means we have this Ci0 as the same type as Ci1 over C less than I, and then less than 2. That's one thing. Second one is that the first column is consistent. This is consistent. And the third thing is that the second column is Ci1 is K inconsistent. Okay, I just remind you the definition, okay? So first of all, yeah, maybe now I'll just try to go this way. So first of all, I want to assume that replace omega by the rationals and assume that Ci, let's put Ci less than 2. This thing is indiscernible. Okay, everything is okay when you go to indiscernible sequences. I mean, when you extract an indiscernible sequence from this omega sequence, it retains all these properties of having the same type and consistency and K inconsistency. Okay, so we're allowed to assume it. And okay, so let n be some natural number, and I want to look at this family of formulas gamma n, which is going to be phi of x Ci0 for I in the open interval 0 n, but excluding all the natural numbers. Okay. Union phi of x and ci1 for I less than n in the natural numbers.
We actually I in
Yes, yes. Yeah. Mhm. So the drawing again is so gamma n is like, so let's say we have this is the line of numbers. Okay, and this is 0 and this is 1 and this is 2. Okay, and this is n here. And gamma n is this thing. It's like on the 0 path we take. Okay, so this would be ci0, and on the 1 path we just take this guy. Okay, this is the kind of a drawing. I hope it helps. Okay, so first of all, gamma 0 is consistent because it's just an empty set. Okay, I'm just gamma 0 is empty. There's nothing there. It's just empty. Now gamma k is inconsistent because gamma k includes k instances of this guy, and we assume that this guy is k inconsistent, right? So gamma k is inconsistent. Okay, so so by compactness, there is some S subset of the interval 0, 1, finite. Yeah, in the rationals, everything in the rationals. Such that, finite, and some delta of x subset of, wait. So I think I forgot to say something important. Yes. Here, let n less than k be maximal such that gamma n consistent. Okay, so there is some n. Okay, there is some n such that gamma n is consistent, but gamma n plus 1 is not consistent. Okay, I forgot to say that. Okay, so delta of x is some finite set of formulas.
With gamma or
Gamma n, yeah, gamma n. Sorry, such that delta of x union phi of x, c, and 1 union phi of x, c, n plus s0 for s in not s, call it I in S is inconsistent. Okay, so we know that gamma n is consistent while gamma n plus 1 is not consistent. So gamma n plus 1 is the same as gamma n union phi of x, c, and 1 union phi of x, c, and 0 I0, where I is in the interval n plus 1. So we know this thing is inconsistent. This is gamma n plus 1. We know this thing is inconsistent, so we can find the finite set here and the finite subset here such that this is inconsistent. This is all I'm saying. Okay. Yes. Okay. So now now I'm going to apply this lemma. So I have to find high 1 and high 2. So high 1 of xy will be phi of xy and sorry, that's it. That's going to be yeah. 2 of xy xz, high 2 of xz is going to be delta of x, and so this delta is a finite set, but we can just put conjunction here on all of delta. So delta of x and phi of x zi. Okay. That's good. That's He1 and He2. Okay, so these are going to be guys witnessing inconsistency. Okay, and now this. So I defined what the He's are, and now I need to define the array. So let EK0, sorry, EK0 is the same as CK0, and EK1 is CK1. So first I define the e's. Remember that in this lemma we had with these and e's. Okay, so first I defined what the e's are. The e's are just the c's that we have.
This is the same K or
What? For each k. Yeah, for
okay, so
for-
maybe not K.
Oh, right. There is some k. So I am n. Okay, n and n. Right, because k was the k for the k inconsistency, right? And then, but that's not going to be used again. So anyway, this is the EM0, EM0 and EM1, and now I have to define the DK0 and DM0 and DM1. So DM0 is going to be CK plus I. Yeah, CK plus I0. Okay, M. I copied from my notes. In my notes it said K. Okay, and DK1 or DM1, sorry, actually DM1, it doesn't matter. Because actually in the proof, if you remember, actually in this proof, we never use the, they don't play any role. The DK1, we don't care about those actually. I could have stated it without mentioning it. Yeah, and that's it. So now it's just checking that everything works, that we get the consistency and inconsistency that we want. Yeah. Okay. So yeah, I claim, for example, so let's look at this. Okay. So I'm saying that EM0. I want to say that EM0 is the same type as EM1 over what? Over C, over the pairs. So in this case, it will be everything E less than M0, E less than M1, and then as well the right, and D less than M0. That's what I need to show. That's I'm just copying what one says. Okay, so I'm copying. If I copy one, then I get exactly and this. And this is true because this is the assumption of the SOP1 array, right? The E's are actually the C's, and this is a subset of what they have the same type of even things, right? Because because here I took all the rationals and yeah, so one holds, and the consistency of psi, which is just, remember, psi is the conjunction. So one is okay. So so this is okay by assumption, by this assumption, I mean. Two, the consistency follows from the assumption two. So actually one corresponds to one, and this follows from two. So this one follows from this one. This two follows from these two, and three, this three follows from the choice of S and delta. Okay, that's the inconsistency. If you plug it in the drawing, you will exactly see that we get three, and all the indiscernibility going around. Yeah, actually, I have time. Maybe I can explain it a little bit more. Probably, it's right? Yeah, it's okay. If people want more explanations, or that's yeah, you want. Yeah, okay. So yeah, so maybe just a drawing. Yeah. So the drawing is we have we have this C, this is C0, and this is C1, and delta, what is delta? Delta is taken from somewhere. Yeah, delta is taken from here somewhere. So delta of x is some conjunction of guys from here. This is something from here. Okay, delta is something from here. Yeah, and yeah, and here I have this is C0, this is C1, and right. And now, yeah, here I have like if yeah, I want to say that high 2 and high 1 are inconsistent. So high 1, this is like living in this blob here. This is high 1, and high 2 is exactly saying like if I take somebody from here satisfying high 2, so high 2 is this delta, and yeah, wait. Yeah, yeah, right. That makes sense. And this should work, but it's really hard to do it on the board. But right, what is high 2? So let's just check it formally, okay? So I want to show that so 3. Let's check 3. So let's say we have j less or equal than I, and I want to show that high 1 of x is I0 and high 2 of x e j1. I want to show that this is inconsistent. That's what we want. Okay, so let's just check what are the e's and the d's. So yeah, I think I might have. Did I mix up? So yeah. No, it does work. Okay, so this just says phi of x cj1, right? Because ej1 was cm1. I'm just copying. Okay, what does this say? This says no. I think, yeah, maybe I mixed up high 1 and high 2. Wait, I mean, yeah, I think I probably mixed it up. Yeah, let's change it. Yeah, I think I should. This is this is one. I think I mixed it up. This is. This makes more sense, right? Yeah, the e's. Yeah. This way, this makes much more sense because of the choice of the d's that I put here, and these are it just doesn't make sense otherwise, right? So the d should come into high 1. So high 1 should be this. Yeah. Okay, right. I just mixed up high 1. Okay. So after I fixed my mistake, I got that high 2 is this, right? Because now I changed it. Right, high 2 is phi, and this is this, and this is just this. Now, what about this guy? This guy is the conjunction of delta of x, which doesn't change. Okay, these are the parameters we have. So this delta is over some fixed part from gamma n, and this is going to be the c that we're going to use. Okay, that's going to be the parameters. So delta of x and the conjunction on I in S of phi of x. What did you say di0 is? Yeah, c. There's a problem here.
Cm plus I?
Yeah. L. That should be L in S. What was the question? Yeah, because there's already I, and I can't use the same one. So
Yeah, I see.
Yeah, that should be the C. I plus. What did I say here? Yeah, I plus L for L in S. Yes. Okay.
Zero.
What? Oh, yeah, there's a zero involved. Yes, zero. Thank you. But okay, but now we win because we know this two is inconsistent. That's exactly the definition.
What do we win?
What?
What do we win?
We win the proof of the lemma. So that's it. We win. Okay. Okay. So so yeah, now we have these two things that are equivalent. Okay, so I have like 15 minutes, so maybe I can prove things a little bit more.
We had the whole goal. We had the whole goal up there, right?
I have a whole, yeah, exactly. It was like a 5-step plan. So yeah, which board should I go now? This was this one, so I should go to this one. Okay, so yeah, so this is really nice, and let me.
You're actually going to use these both calculation,
What do you mean both?
the array and the tree.
And the tree? Oh yeah, no. Actually, in the proofs, I think mostly we use the array in the end. Yeah, I can't think now of a proof that just uses a tree directly. It's much easier to use that. If you want to prove that something holds in an SOP1 theory, you want to get a contradiction to this. So it's much easier to get a contradiction to the SOP1 array than the tree, because the SOP1 array a priori has this k. I mean, we needed some argument to go from 2 to k. So we hope this argument like saves some time. Okay, so
If you start with a 2, still a complicated proof.
no, then I think it's not complicated. Yeah, but how do I in general know that you got 2? So, right. So I'm going to repeat this, but okay, let me just ask you some questions, you guys. So, is it okay if I talk? So, do you know what an invariant type is? So, invariant types. So, is it okay if I say Q? Like, let's say if I say Q of X is a global type, which is A invariant. Is that okay with you guys?
Just say what it is.
It's just a type, such that every automorphism. So it's a global type. It's a type over the monster model. Such that every automorphism that fixes A will fix this type setwise. Okay. Okay. Now so I'm going to put some stuff here, and then the second question I have is it okay? Suppose Q and P. So you have Q of X and P of Y. These are A invariant. Then I want to say what is Q of X product, tensor product P of Y. And I want to say this is a type in 2 variables, which is also A invariant. So this definition might not be so well known, or is it?
Just say it.
I can just say that as well. So what is this? Yeah, I know, but okay. So this is just the union over all subsets B containing A of the type of AB over B, such that so B realizes P restricted to B, and A realizes Q restricted to B. Okay. And yeah, okay, there's something to prove it. You have to show that this is a complete type. And actually, it's not only that it's a complete type, it's also, it doesn't, so you have to show this doesn't, the choices of A and B here doesn't matter. It will give you the same type. If you choose any other A and B, this will be the same. And this observation tells you that this union is consistent because of the choice, because the choice doesn't matter. This means that the union is consistent. And moreover, the union is also invariant. So you get this, and
maybe it's worth pointing out that if you take a global type that's a variant, and it extends to connect.
Oh yeah, right. Yes. Right. So another way, which is the same as saying the type of AB, where B satisfies Q over the monster, and A satisfies
over the monster.
P satisfies.
wait. No, P. P over the master, and A satisfies Q over the master and B. Where now I think of it as living is a bigger subgroup.
In the type over the monster, AB over the monster.
Oh, yes, thank you. Okay, yes. So yeah, that's another way to do it. You can because like Anand said, every invariant type extends uniquely to an invariant type over any other extension.
And you still have to prove that it doesn't depend on the source of it.
Yeah. And you have to show that it's independent of the choice of A. Right. Okay. Now a related thing you can do is you can take the product of P with itself. So you define if P is a invariant, we can define P to the alpha, let's say, for any ordinal alpha by induction. So this is going to be P to the alpha is going to be an invariant type in the variables x beta beta less than alpha. Okay, it's going to be an invariant type over the master model in these variables, and yeah. So the way you define it is you just say that P, okay, P1, okay, we're going to start from 1. So P1 is just P, and P alpha plus 1 of is going to be, yeah, it's going to be P of x alpha, tensor P of to the alpha of x less than alpha. Okay. And for alpha limit, we take union. So P alpha is the union of P beta. So actually, we can also we don't really need to define it for every ordinal. We can just define it for the natural numbers, and then for every ordinal to just be the limit because of the following observation that I'm going to say. And now is that if a sequence satisfies P to the alpha, then it's indiscernible. So the observation is that if A alpha, A beta satisfies P to the alpha, then let's call this I is A indiscernible. Okay, so we get this way. So this connection between invariant types and indiscernible sequences is really nice because it's really useful.
So, of this living in the master model or living outside the master?
Yeah, okay, I was a bit, so over any B, which B contains A. Or you can think of it living outside. But no, let's not think about it as living outside, okay? What?
You want A in the symbols.
But I'm saying any B containing A. Ah, you're saying that it just follows because it's also B in the symbol. You're saying I can put here A instead, and it's the same. Yeah, it's the same generality. Yeah, sure. Yeah, this even B in the symbol. Yeah. Yeah, keep it. Because all these P's are also being invariant, like you were saying. So yes, and now okay, so these are really nice types then because you can get easily indiscernible sequences. But there's a how do you call it? A reservoir of invariant types we can get from using ultrafilters. So how to get invariant types? Ah, you did. Okay. Okay, so given any model and P of X is a type over the model, then there is a global type R of X containing P of X, global type, which is such that R is actually finitely satisfiable. Fs is finitely satisfiable in M. And it's easy to see that any type which is finitely satisfiable in a set is also invariant over that set. That's a really easy exercise. Okay, so this R will be in particular invariant. In particular, R is invariant. Right. So this is what something that Anna did. It's not a difficult proof at all. You can do it. The easiest way to do it, I think, maybe not the easiest, but one way to do it is to know that if you have a type over a model, then actually it's finitely satisfiable in a model because it's a model. Every formula in the type is realized in that model. So this gives a filter on this model, and this filter can be extended to an ultra filter on all subsets of the monster. And this ultra filter gives you a way to define this global type, which will be finitely satisfiable. Okay, now why am I telling you all this? Because next time I want to discuss Kim's lemma and Kim dividing and Kim forking and so on. So I need the notion of invariant types to do that. So let me just, I'll just state the statement of Kim's lemma without proof, and next time I'll prove it. Okay. So Kim's lemma, it's very easy. It's an exercise. You can think about it all week or just read the paper. But anyway, I'm going to say it, and next time I'm going to prove it. So Kim's lemma says, so suppose T is N-1 for Kim dividing. Yeah, but I didn't define Kim dividing yet. But so I'm going to state the lemma without.
When you say Kim's lemma, you're not saying it's a lemma to the kids.
Yeah. To Nick maybe, but yeah, but it's the analog of what I called Kim's lemma in the previous talk. Okay, and it'll be clear next week, but I can state it without mentioning Kim dividing here. So suppose T is N-1 and M is a model, and yeah, and phi of x, and let's say that suppose P of x and Q of x, P of y and Q of y are global M invariant types such that P restricted to M equals Q restricted to M. I'm assuming this. I have two global types that happen to have the same restriction through the model. Then, if okay, let AI this will be a realization of P to the omega restricted to M, and BI will be a realization of Q to the omega restricted to M. So we call these are, now we know these are indiscernible sequences because of this. Then phi of x AI is inconsistent if and only if phi of x BI. Okay, so the lemma says that if I have two, these sequences are, by the way, called Morley sequences. Okay, if I have two Morley sequences in invariant types that share the same type, the same complete type over the model, then this set is inconsistent if and only if this set. So in other words, this sequence witnesses dividing, if you remember, like I mentioned last week, dividing. In other words, this sequence witnesses dividing if and only if this sequence witnesses dividing. So it's an analog of Kim's lemma for a suitable notion of dividing, which means dividing with respect to invariant types. It says that any sequence like this will witness dividing. Okay, so next week I'll do the proof of this. It's, as I said, it's pretty easy from what we did today, and I'll give some consequences, and hopefully maybe I'll prove symmetry as well. Okay, thank you.